A RAM read takes 100 nanoseconds. A disk read, even on the fastest SSD you can buy today, takes 100,000 nanoseconds. That is a 1,000 times difference. And that single gap is almost the entire reason Redis exists. But here is the part most tutorials skip completely. RAM speed is only half the story. The other half is a design decision that looks completely wrong on paper. Redis is single-threaded. One thread. No parallelism whatsoever. And somehow, it handles hundreds of thousands of requests per second. Today, we are going to understand exactly how. We are going to go inside Redis, the memory model, the event loop, and the expiry behavior that almost nobody explains correctly. By the end of this video, you will understand Redis at the level that actually matters, whether you are using it in production or walking into a system design interview. I'm Piyush of Code with Clarity, Senior Backend Engineer, and on this channel, I break down how real production systems actually work, not just how the docs say should. If that sounds useful to you, hit subscribe to follow more of our videos. Alright, let's get into it. Why RAM changes everything? Let's start with the obvious question. Why is Redis so much faster than a regular database? The answer starts with where data lives. When your PostgreSQL query runs, your database fetches pages from disk. Even with caching and SSDs, there is always some disk I/O involved. And disk I/O has latency, sometimes microseconds, sometimes milliseconds. Redis skips all of that. Every single key lives in RAM. When your app asks for a value, Redis goes to RAM. That's it. No disk seek. No page cache miss. No I/O wait. To make this concrete, RAM access takes about 100 nanoseconds. For SSD access, it takes about 100,000 nanoseconds. And network round trip, about 500,000 nanoseconds. That's why a Redis get can return in under a milliseconds, even under load. The physics of memory are on its side. But here's the thing. This also means Redis is bounded by your available RAM. You can't store more data than you have memory. That's a real constraint, and we'll come back to that. So RAM explains the speed, but it doesn't explain how Redis handles thousands of concurrent connections without collapsing. That's where the single-thread design comes in. Why is single-threaded a feature? When engineers hear single-threaded, they usually think bottleneck, limitation, and poor design. Redis is single-threaded by deliberate choice, and once you understand why, you'll see it differently. Here's the problem with multi-threading in a data store. The moment you have multiple threads accessing shared memory, you need locks. You need to coordinate. Thread A is reading this key, and thread B, wait your turn. Locks mean contention, and contention means threads sitting idle, waiting. And the coordination overhead, acquiring locks, releasing them, handling deadlocks, that overhead adds up fast. Redis says, forget all of that. One thread, one command at a time. Here's what Redis event loop actually looks like. Accept incoming connections from clients. Number 2, read the command from the socket. Number 3, execute the command in memory, so no I/O. And 4, write the response back, and then repeat. Because every operation is in memory, no waiting on disk, no I/O latency, each command takes microseconds. The thread moves through thousands of commands per second without ever blocking. No locks, no contention, and no coordination overhead. This is why Redis can feel faster than a multi-threaded system that should theoretically have more throughput. The overhead of coordination in that system costs more than the parallelism gains. Now, is there a catch? Yes, one big one. If you run a slow Redis command, something like keys, asterisk on a large dataset, or a poorly designated Lua script, you block the entire event loop. Every other client waits. This is why Redis has a list of O of N commands you need to be careful with in production. The lesson: Redis single thread is a strength for fast operations and a liability for slow ones. So design accordingly. How key expiry actually works. Okay, this is the part I want you to pay close attention to because this is the part that trips up even experienced engineers. When you set a TTL on a Redis key like set session :user123 x3600, what do you think happens when that TTL expires? Most people assume Redis has some kind of background timer. Every second, it checks all keys, finds the expired ones, and deletes them. That is not how it works. Redis uses two mechanisms for expiry, and they work together. Mechanism 1, lazy expiry. When a client requests a key, Redis first checks, has this key expired? If yes, it deletes it right then and returns a miss. If no, it returns the value normally. That's it. The key isn't deleted when the TTL hits. It's deleted the next time someone asks for it. This is called lazy expiry. Redis isn't lazy about cleanup. It only does work when work is needed. Mechanism 2, active expiry. But what about keys that nobody ever requests again? They'd sit in memory forever with lazy expiry alone. That's a memory leak. So Redis runs a background job 10 times per second that samples 20 random keys with TTLs. If more than 25% of those sample keys are expired, it runs the sampling again immediately. Otherwise, it waits for the next cycle. This is probabilistic, not exhaustive. Redis never guarantees that all expired keys are deleted the moment their TTL hits. It guarantees eventual cleanup with bounded memory overhead. Now, why does this matter in practice? It means if you have 10 million keys all expiring at the exact same second, a common pattern with session stores after a bulk import. Redis will not try to delete all 10 million at once. The event loop won't freeze. Active expiry will clean them up gradually over the next few cycles. But it also means you should never rely on Redis expiry for anything that requires precise timing. If your business logic says, delete this exactly at 3 p.m., Redis is the wrong tool for that job. Design your systems with the assumption that a key might survive slightly past its TTL. That's the contract Redis gives you. When not to use Redis. I want to talk about something most Redis tutorials skip: when you shouldn't use it. Because Redis is genuinely excellent at what it does and genuinely bad at things outside that zone. Don't use Redis when your data is larger than available RAM. Redis is in memory. If your dataset is 200 gigabytes and your server has 64 gigabytes of RAM, Redis is not the answer. Look at disk-backed stores. You need complex queries. Redis is a key value store with some data structure support. If you need joins, full text search, or complex aggregations, that's not Redis' job. You need the expiry to be exact. As we discussed, Redis TTL is eventually consistent. If your use case needs precise to the second deletion, you need a different mechanism. The engineers who use Redis best are the ones who treat it as a specialist tool: caching, session storage, leaderboards, pub/sub, rate limiting, and not a general purpose database. So let's recap what we covered. Redis is fast because everything lives in RAM, 1,000 times faster than SSD. It's single-threaded not despite being fast, but because of it. No lock contention, no coordination overhead, just a tight event loop executing commands in microseconds. Key expiry is probabilistic, lazy on read, active in the background. Never assume a key is gone the moment its TTL hits. And like every tool, Redis has a zone where it's exceptional and zones where you shouldn't use it at all. I've also written a full breakdown of this on Medium. Link is in the description. It covers the internals in more depth if you want the written version. If this was useful, subscribe to Code with Clarity. I break down one backend or system design concept every week at the level that actually matters for real systems and real interviews. See you in the next one!